Okay. Yeah, so here's the problem. It's from 2020 February, silver, and it's called Clock Tree. So we have a barn with n rooms, and we're given the bound is 2,500, and then the n rooms are numbered 1 through n, and we have n minus 1 quarters that connect pairs of rooms. So we also know that we can go from any room to any other room, which is pretty important for the solution. Yeah, so we're going to, basically Bessie is going to go around all the rooms, and each room has a clock that points to a number, an integer 1 through 12. And every time she goes to a room, she's going to advance the integer that it points to by 1 in that room. So basically everything works as you think it would, and then 12 goes to 1, and then 1 to 2, and so on. And yeah, so we're asked for the number of rooms that Bessie can start in so that she can somehow get every clock to point to 12. And they give us a small clarification that like the initial room that she's in won't be advanced until she potentially goes back to it. Yeah, that's pretty much it. We have a sample test case. So this is n, and then these are the 4 initial clock numbers, and these 3 are the different quarters. So yeah, the first thing that we notice when we read this problem is that we have these rooms that we can treat as nodes, and then quarters that connect rooms, so they're like edges, which means that we're pretty sure this is going to be a graph problem because we have nodes and edges between them, and we're traversing a graph. And also, the fact that we have n rooms, so n nodes, and then n minus 1 edges between them, and we can reach every node from every other node means that we have a tree specifically. So yeah, I think if you've seen trees like a few times, then you can probably see this. Also, the name of the question is clock tree, which is nice. So yeah, a tree is basically a graph with a root and a bunch of edges, and each node is going to have like one parent, and it only has a connection to one other, or sorry, yeah, it only has one parent, sorry, never mind. And then this is where we get like the n minus 1 edges, because if we have n nodes, each one has a parent except for the root over here. So we have n minus 1 things that have parents, so n minus 1 edges. Yeah, okay. So now, I guess we just kind of think about like the condition that we're given, that she increases the clock number by 1 each time she goes to it. So we're going to define a array, I guess, or a variable. So the time after she traverses C quarters of room I. So this is the time that the clock in room I is showing after she goes through C rooms. And we know that every time she's going to increase one of the clocks by 1. So I think one like kind of natural thing to look at now is the sum of the TCs over time. Basically, the sum of the numbers or the times that the clocks show over time or as she traverses more corridors. And we're going to take this mod 12. This is a small detail, but yeah, because it's 1 through 12. So we know that this thing is going to increase by 1 each time because we're increasing 1 clock by 1 each time. But the problem is that this doesn't really give us that much information because, like, let's say if we start at node 1, then we're going to make this the root of our tree. Then the sum of the TCs over all the rooms I is just going to increase by 1 each time. So we don't really know like whether or not we can get to a desirable sum because we just know it's gonna, like we already know exactly what it's gonna do, but not that much about like the numbers themselves. Hopefully that kind of makes sense. But yeah, the idea instead of using just the sum is that we're gonna use the alternating sum. So alternating is not in the sense of like the node numbers, like we're not going to do TC of 1 minus TC of 2 plus TC of 3 and so on. This might be the case, but we're actually going to define it a different way. So we're going to use a distance function. So we define dist I to be the distance of room I to the root node. So basically we're just going to like add all of the TCs of i's that are even distances away from the root and then subtract those that are odd distances away from the roots. And you'll see how this is helpful in a second. So yeah, to kind of quantify this, we let SC for S for sum, and then C is just, as before, the number of corridors we've been to. We're going to let this be the sum from 1 to n, so this covers all the rooms, of -1 to the distance, -1 to the distance of room I, and then times the value that it shows, and then mod 12. So yeah, if we list out like some values of this for small c, we have S0 is equal to the summation, and then we know that T0 of I is just the number that it, like each clock starts at. So yeah, basically we're just going to take the alternating thing of like the starting numbers. This part is pretty self-explanatory. What's interesting is if we look at S1 in terms of S0, So as we said before, we're going to go to another node and then increase that time by 1. So if we have this as the root, and then we're going to a different room now and adding 1 to the time here. And we know that this node is distance 1 from the root because we just came from the root. So this is odd, which means that we're going to have a factor of -1. So the, like if we say this is index I, room I, then the term for this is going to be -1 to the 1 times T0 I in S0. But in S1, it's going to become -1 to the 1 times T01 plus 1 because we're increasing it. And this is just the term in S0 minus 1 from this -1. So yeah, what this means is that everything else stays the same because we haven't gone to those rooms or like messed with those clocks, but we're subtracting 1 from this term. So overall, S1 is S0 minus 1. Okay, so same idea. If we go from S2 and write it in terms of S1, we are going to a node that is distance 2 from the root and then adding 1 to it. Either this or we're going back to the root, which is distance 0 from the root. The only thing that we really care about is the distance function's parity. So it's the parity of the distance to the root is always going to change each time, which means whether or not we go to the second node or if we go back to the root, it's the same parity. So this is going to be S1 plus 1 instead because we're going to have -1 to the 0 or -1 squared and then times +1. This is how much we're going to change the total sum. And yeah, you can see there is a very obvious pattern in here. If we write this as like one big equation, we have S0 is equal to S1 plus 1 from here. And then S2 is equal to S1 plus 1 as well. And then this is also S3 plus 1, which is equal to S4, and so on. So this is pretty nice because now what we know is that for some S, we don't really know when, like after some amount of corridors that best C traverses, we're going to get to a sum of 0. And this is because at that time, what we want is that every clock reads 12, which is 0 mod 12. So we're going to multiply by 0 mod 12 in each term, so the whole thing is going to be 0 mod 12. So we know this thing is equal to 0 at some point for some question mark C, or the number of corridors. And this is either equal to S0 or this thing plus 1 is equal to S0. And we want this thing to be 0, so this is going to equal to 1, which means S0 is 0 or S0 is 1. So in order for us to be able to get to the desired state, we need to have S0 equal to 0 or 1. So this is our necessary condition. And you can see that like S0 is very, or I don't know about very, but like you can find it without doing too much work, because the formula of this, we already know all the t-zeros, it's just what we're given. And then the distance, the way we find distance is we can do like a DFS or a BFS and just find the distance to every node. So yeah, now we know this is necessary, but we also, in order to like make sure that this is sufficient, we should prove it just for completeness. And we're going to do this with induction. So we want to show that if S0 is 0 or 1, then we can get all 12s. So the base case, we're given S is between N is between 2 and 2500. And if N is 1, the problem doesn't really make sense because you can't really go anywhere from that one room. But we can check that if N is equal to 2, then we either have like 2 nodes that are the same or 2 nodes that differ by 1. So like 10, 10 becomes 10, 11, 11, 11, 11, 12, 12, 12. This is when S0 is 0. And then when F0 is 1, then we're going to have like 11, 10, for example. These two differ by 1. And then we can do 11, 11, 12, 11, 12, 12. So both of these are possible. You can say this rigorously, but I think this is pretty easy to see. So for the inductive step, we're going to basically take, let's say if we have a room R, and we define R so that this room is a leaf. And a leaf is basically something at the bottom of the tree. So like this one, and this one are all leaves because there's nothing underneath them. They're only connected to one node. The reason we do this is so that once we get rid of this node, it doesn't affect anything else beneath it. So what we can do is if we start from 1 and go to room R, and we basically just keep traversing all of the corridors on this path, and then go back to 1, so 1 to R, back to 1. And we do this cycle over and over until R is 12. Or sorry, not R. The time it shows at some point is equal to 12. So now that we have R is satisfied, we don't really care about it anymore. And then because there's nothing underneath R, we've essentially removed it from the graph, so we can just deal with this. But this thing only has n minus 1 nodes if we started with n nodes. So what this is saying is if we have n minus 1 works, then n works. And this is what we need for induction. So yeah, we're done proving that this is sufficient. We can go through and like calculate this S0 either using this formula for each possible root node or starting point, or we can notice that, like, for example, if we can start at 1 and be able to get to what we want, then we can start at anything that's an even distance from 1, because then all of the distances are going to be the same parity as before. So we can do that for 1, and then a thing that's an odd distance from 1, and then just count all of them and add them up. Another way of thinking about this problem is using bipartite graphs, but I'm already kind of over time. So yeah, it's really not that like necessary. It's just for the distance function. You can frame it as like this tree becomes a bipartite graph with different levels. So this is distance 0, 1, 2, 3. These two are the same side, and these two are on the same side. So yeah, that's it. I hope that helps.